D. This is where we're going to start the calculations. So the first thing we have is, much like the KAs and KBs, there's a chart associated with this that there's one posted online. And so I will give you KSP values, or when you're doing mastering or problems in the book, use the charts they give you, because once again, they will vary occasionally from source to source. So solubility product is an equilibrium. So it's like the other equilibrium. You're going to set up an ICE table. The ICE tables become much more critical because, unlike the acid-base ones where we only had one proton at a time, we can have multiple values of X. So you could have 2X, you could have 3X, you can even have 4X. You're going to use the polyatomic function in your calculator again, and it may be greater than X squared. So if you've programmed in for strictly X squared, then you may have a problem. I will try to limit these. We can make the assumptions. I'll show you how to do that. And the trick to these really is making sure that you use the value you get in the E value of the ICE table and not to vary them. Because one of the issues that people have, and I'm not going to lie, I was one of these when I was in your chair, is that you look at it and go, well, wait, that's just got to automatically double, when it may not have a double in the ICE table. So be careful when you work that. So let's work our first one. The first one is the Ksp of calcium sulfate. All right, so calcium carbonate. That's your solid. We're going to set up our equation. It's going to be calcium 2 plus carbonate 2 minus. We know that our Ksp is going to be equal to 2.8 times 10 to the minus 9. It was given. And we want the solubility of the calcium carbonate in moles per liter and in grams per liter. Now, the reason why it's done in moles per liter and grams in liters, but particularly grams per 100 milliliters, is that's basically the standard way it's put into charts. It's where, you're talking about the same thing. So if you say the solubility is 5.2, then the assumption is this grams per 100 milliliters. Whether you're talking to somebody in England or Australia or China or wherever, that's the standard by which you do it. So, how do we do this? Well, we set up our ICE table. Initially, we start with 1 here, 0 here, and 0 here. We're going to lose X, but as long as we still have the solid, our value is still 1. This value is your solubility, is what it boils down to. Okay? And so the calcium is you're going to gain X here, gain X here. It's going to be X and X. So your Ksp is going to be equal to your calcium times your carbonate, which means we replace each of those with X. And our value for Ksp is 2.8 times 10 to the minus 9. So X squared is equal to 2.8 times 10 to the minus 9th. So the opposite of the square is the square root. So X comes out equal to 5.2915 times 10 to the minus 5th. And that would be moles per liter, or molarity. So that's the answer to the first one. So we'll put it in nice terms. 5.2915 times 10 to the minus 5th molar. So that's the first one. However, we want it in grams per 100 milliliters. So if we want it in grams per 100 milliliter, and we start with 5.2915 times 10 to the minus 5th moles in 1 liter, then we know that instead of being 1 liter, we're going to need to multiply it by 0.1, and Then we'll need the molecular weight, which is 136.1416 grams per 1 mole. So that means that we end up with 7.2039 times 10 to the minus 4th grams dissolved in 100 milliliters. So that's our value there. Now, let's go back. I told you before that you might have something greater than x squared. Now remember, to do x squared, that's the opposite is the square root. Okay, if you have x cubed, then the way you can do that is x raised to the 1 divided by 3 power. That is one way to do it on your calculator, or you can use the cube root. It doesn't matter. Most calculators have square root and cube root, but when we get to 4s and 5s, I find it easier to raise it to the fraction. Okay, so this is your algebra note. And remember, algebra hangs on to whatever we're doing here. Okay, so the next one is copper 2 oxide. And in this one, we're going to, small amount to dissolve concentration. We want to calculate the Ksp here. So it's copper 2 oxide, copper 1 oxide. So it's 2 copper plus 1s plus oxygen 2 minus. And we do our ICE, and remember it's 1, 0, 0, minus x plus 2x plus x and 1. So the final value here is x and x. Now, we're looking for our Ksp. Our Ksp, remember, is equal to the copper value squared times the oxide value. Okay? Now, we can't have two unknowns, and this is what we're looking for as our unknown. But we're told that this copper concentration equals 2.7 times 10 to the minus 5th. That means that it's equal to the 2x. So this is my copper, which is true, but my x value is equal to 2.7 times 10 to the minus 5 divided by 2, which brings us over here, which is 1.36 times 10 to the minus 5th. So if we go back in here, and our Ksp is equal to the 2.7 times 10 to the minus 5th. Remember, use the value we're given, squared, times 1.36 times 10 to the minus 5th. Then you'll do the math. Again, be careful if you're using your calculator, if you're not using the EE function, and you'll get a value. Okay? And the value comes out equal to 1.00618 times 10 to the minus 14th. So your Ksp value is 1.0062 times 10 to the minus 14th. And remember, K values have no unit associated with them. Okay, it's really simple and it's really straightforward as long as you keep up with your ICE table. Your ICE table is your friend. Okay, limitations of solubility product. You may want to read over this. Again, it won't be a bonus question, but it's worth your time to look over the problems in the text as well as these little trivia things.